Good afternoon. Today I'm going to go ahead and be proving the following Diophantine equation for my number theory class. I'm going to go ahead and prove that x to the fourth plus y to the fourth is equal to z to the second has no solutions. Okay, and we're going to go ahead and start. Okay, to begin, first of all, we need to know the following three things. We need to know theorem 1, lemma 1, and lemma 2. I'm going to be going to use the following three in my proof, so it's good to know this, or you can go ahead and backtrack to the video and verify for yourself as to why I'm using the theorem, the lemmas. Okay, so I'm going to go ahead and screenshot it for you just in case you need to backtrack. This is theorem 1. This is lemma 1. And then this is lemma 2. Alrighty? So we're going to go ahead and start. So, to start off, I'm going to go ahead and be proving this by contradiction. Okay, I'm going to go ahead and start. I'm going to assume that x to the fourth plus y to the fourth is equal to z to the second has non-trivial solutions. What does this mean? This means that it has solutions that don't equal 0. Where x, y, and z are in the positive set of integers, and without loss of generality, the GCD of x and y is equal to 1. Okay, I'm also going to suppose that x sub 0 is equal to x, y sub 0 is equal to y, and c sub 0 is equal to z. And this is a solution of the Diophantine equation where x sub 0, y sub 0, z sub 0 is in the set of positive integers, and again without loss of generality, the GCD of x sub 0, y sub 0 is equal to 1. So what we're going to go ahead and do now is basically plug in x sub 0 for x, y sub 0 for y, and c sub 0 for z. And once we do that, we're going to go ahead and get this. Okay, we went ahead and substituted, and substituting, we get the following. Okay, and we're going to go ahead and rewrite this. I want to go ahead and rewrite this like this. Okay, with the power of 4 divided into these two, x sub 0 to the second with to the power 2, y sub 0 to the second to the power 2, and z sub 0 to the second. Okay, where the GCD of x sub 0 to the second, y sub 0 to the second is going to be 1. And why is this so? This is because of lemma 1. Again, you can backtrack, go to the beginning of the video and verify for yourself, but I also boxed it in for you so that you can verify this. Okay, now once we have that, we can now say that x sub 0 to the second, y sub 0 to the second, and z sub 0 is a primitive Pythagorean triple. Why is this? Again, I boxed it in for you. This is because, for example, if p is divisible by x sub 0 to the second and p is divisible by y sub 0 to the second, then p will also be divisible by x sub 0, and p will also be divisible by y sub 0. In other words, if a number divides the square of a number, then it divides the number itself. Okay? Now this contradicts the GCD of x sub 0, y sub 0 equaling 1. Thus, x sub 0 to the second, y sub 0 to the second, and z sub 0 must be a primitive Pythagorean triple. Okay, once we have that this is a primitive Pythagorean triple, we can go ahead and apply theorem 1. Again, if you need to verify what theorem 1 is and why I'm going to go ahead and do this to the following terms, you can do so at the beginning of the video. You can backtrack. Okay, so I'm gonna go ahead and apply theorem 1 for each term, and I'm gonna have it in terms of m and n. Okay, as you can see here, now x sub 0 to the second is gonna equal m squared minus n squared, y sub 0 to the second is gonna equal 2nm, and z sub 0 is gonna equal to m squared plus n squared. Okay, the GCD of m and n is gonna equal to 1. Okay, and this now creates a set of solutions for the following equation. Okay, and we can now use our first equation to find m squared. Okay, what does this mean? I'm gonna go ahead and find m squared from this. I went ahead and did that for you. As you can see, m squared will now equal x sub 0 to the second plus n squared, and then the GCD is of m and n is equal to 1. And since this is so, we can now, I'm sorry, let me move this right here. we can now say that x sub 0, n, and m is a primitive Pythagorean triple where m is odd and n is even. And again, this creates another Pythagorean triple, and we can again apply theorem 1. Okay, so I went ahead and applied theorem 1 once more. And as you can see, I used it in terms of r and s. So now x sub 0 is going to equal to this, n is going to equal to this, and m is going to equal to this. Okay, GCD of r and s is going to equal to 1. And again, this creates a set of solutions for the following equation. Okay, now I do want you to recall that by doing this, okay, since we have m is odd, n is even, and the GCD of m and n is 1, we can also say that the GCD of m and 2n is 1. Why? Because we can replace n by 2n because n is even, okay? And so it's like saying the same thing, okay? So now we can go ahead and go back to our original, one of our original terms here, and we can replace this n by 2n, as I did, okay? Now doing this, we can apply lemma 2, and we can get that m is equal to z sub 1 square and 2n is equal to w square, okay? Where z sub 1 and w are in the set of positive integers. Now, as you can see right here, for the 2n equaling y square, we have a perfect square here, and we do have to prove this, okay? So our goal right now is to show that n is a perfect square in terms of r and s, okay? I went ahead and I let w equal to v, where v will be in the set of positive integers, and I went ahead and solved for v. Okay, solving for v, I get w over 2, and then I went ahead and squared the left-hand side, the right-hand side, as you can see here, and I substituted this w square by 2n. Remember the 2n that was here. Okay, I went ahead and substituted that, simplified it, okay? And then this n right here, I went ahead and substituted by rs, okay? Once you do that, you can cancel out these 2's, equaling out rs, okay? And so rs will now equal to v squared, okay? Where the GCD of r and s is 1, okay? So once you do that, let me go ahead and block this out. Once you do that, since rs is now v squared, is a perfect square, and the GCD of r and s is 1, we can apply lemma 2 again, okay? I went ahead and applied lemma 2 again for r and s, and I used x sub 1 for r and y sub 1 for s, okay? I went ahead and did that, and then again, x sub 1, y sub 1 is going to be in the set of positive integers. I do want you to notice that the r and s, the GCD of r and s, is 1, and if that is so, the GCD of x sub 1, y sub 1 is going to be 1 as well, okay? Okay, so I went ahead and we can go ahead and write x sub 1, y sub 1 in terms of the original equation. So I went ahead and did that for you, okay? And then that's going to be equaling out to r squared plus s squared, okay? So now if we look back at our Pythagorean triples, okay, we can see that m is equal to r squared plus s squared, or in other terms, m is equal to z sub 1 squared. Okay, we can write this as a chain of equations, and we can write it as x sub 1 to the 4th, y sub 1 to the 4th is equal to z sub 1 to the 2nd, where x, y, and z are in the set of positive integers, and the GCD of x sub 1 and y sub 1 is equal to 1. Okay, moving on, we can now say we have z sub 1 is less than c sub 0. Why is this? Because of this explanation right here, and you can verify this for yourself. If we repeat this process with a Diophantine equation, we would obtain a positive integer c sub 2, where c sub 2 is less than c sub 1, which is less than c sub 0, okay? This would show that it has no least element, which will contradict the well-ordering principle, okay? Therefore, okay, x to the 4th plus y to the 4th is equal to z to the 2nd, has no solutions. And therefore, we have proved our problem. Okay, thank you for watching and have a good day.